The next slide goes into experiments and simulations with designs of damage-resistant, high-transmission optical thin-film Fabry Perot filters. We start on the input pump laser side of the optical window for the DPAL with an anti-reflective thin film which will allow maximum transmission without much reflections of the input pump laser beam, followed by repeated layers of quarter wavelength of high and low index materials, followed by a low index material, followed by the same high and low index material, then followed by typically a high index material and the thin film or damage resistant optical material. The next slide shows the application of the Fresnel equation in the optical filter as a basis, and as you can see, whereas there are n prime and n, which are indices of refraction of the two media, there is a reflection which occurs for light normal incident to the boundary of the given as n prime minus n squared over n prime plus n squared, where n are the indices of refraction of the two media. Now, radiation is also absorbed inside the optical element by the material. So if there were a x of the material, and an absorption coefficient of the material alpha, what would be the transmission is e to the minus alpha x. And so this is a basis for the design and a lot more sophisticated mathematics and simulation and optimization, and the results are shown in the next slide as far as the design of the high transmission Fabry Perot optical filter. Here we show the design of a damage-resistant high-transmission optical thin-film Fabry Perot filter, modeling and simulation results using MATLAB. And so we use a quarter wavelength optical thickness. The substrate is, for example, fused silica. Then we have a thin film top layer, aluminum oxide. Our high and low index layers are zinc sulfide and cryolite respectively. Simulation wavelength 0 to 2000 nanometer, and focusing on 700 to 900 nanometer with a midband of between the 780 and 795 input-output of the rubidium laser at in the midband at 785.5. So this is the first one really is just an example of how the particular mathematics can be applied to create a Fabry Perot filter with high and low index material. So at the DPAL input and output wavelengths, we were looking at transmission as high as 99.5 approximately percent at the 785.5 midband region. In the case of the substrate being aluminum oxide, we have zirconium dioxide as being the atomic alkali resistant protective layer, and we decide to use, for example, tantalum penoxide and silicon dioxide as our relative high-low index of refraction materials to create Fabry Perot filter number 2 with high transmission at the 780 and at 795 nanometer. And so in the case of fused silica being the substrate at 1.52 the refractive index, we have zirconium dioxide as being the top layer, and again zirconium dioxide, silicon dioxide being the high-low layer, and we have Fabry Perot filter 3 with transmission as high as uh, roughly 97% at 780 input and output wavelengths. And in the case of the substrate being aluminum oxide, zirconium dioxide, tantalum pentoxide being the high, and the aluminum oxide being the low index material, we have Fabry Perot filter 4, and as you can see, we can get very high transmission above 98% within the range of the DPAL pump input and output beams. So this is just to demonstrate that it is possible to design this filter to have high transmission and also to be damage resistant. So really there are a number of different options when dealing with the metal oxides in terms of the filter, and the decision is what will be the top layer. And so if we use zirconium dioxide, this shows how we can design uh, an optical high transmission filter from this type of material. The next slide shows the MATLAB simulation which achieved those results, and this one in particular is using refractive indices of 1.7 for the substrate, 2.13 for the top film, and high and low film, 2.15 and 1.5 respectively. The optical thickness or quarter wavelength is given here, and our wavelength of interest, the midband, is given. And essentially what we do is we do a sweep 0 to 2000 nanometer range broadband, then focusing on 700 to 900 nanometer range. And so we have we assign a number of layers of high and low index material, and we assign the refractive indices. We inside an array, and we implement a complete transfer matrix array, and then we calculate the optical transmission and plot it. So this would be the example for the Fabry Perot number 2, where the substrate is aluminum oxide, zirconium dioxide top layer with tantalum pentoxide and glass as the high and low layers. In the next slide, we see the optical transmission versus wavelength of the full spectrum. As you notice, there are peaks and valleys. However, within our range of interest, which will be shown in the next slide for the DPAL input pump wavelength of 780 and midband 77.5, and the output at 795 nanometer. What you do show is very, very high optical transmission. In the case of FPR number 2, FPR in this case, we show similar results, and so we can go on FPR number 3, same very high transmission within the DPAL wavelength, and FPR number 4 similarly, very high transmission within the DPAL wavelength. So there are quite a few possibilities as far as the optical transmission, and really the most important thing is to get the top layer, the thin film, the protective layer correct. So on the next slide, to a focus on zirconium dioxide and as a thin film layer. Earlier on, we created a design and ran a simulation with zirconium dioxide. Uh, Essentially, you have silicon dioxide. Both sides of the optical window were coated, and as you can see, the maximum transmission was close to 100% at the wavelength of interest in the midband for the D panel. So in this case, our film thickness was 247.7 nanometer.